Swayam Prabha. Digital India. Educated India.
So, we have discussed the problem of vibration of different types of mechanical systems, and we have now some idea about how to analyze a system to extract information about its behavior or characteristics, that is the mode or the frequency and so on. We also had some idea about that in some industrial or engineering situation, how to either use the theories we have learned to our advantage or to design the systems in a manner so that the desired proper functioning of the machine or the unit is achieved. Towards the end, now I think we will just discuss briefly about how to measure vibration. Now, measurement of vibration and associated instrumentation is a subject by itself. So, therefore, we do not hope to do that in that extensive a manner. Our objective will be here to give a very brief introduction to vibration transducer, that is pickup, which are commonly used. Now, the vibratory response of a system can be expected in terms of various parameters. The vibration is just a phenomena, and its description or the vibratory response of a system, its expression can be done through the various parameters which are associated with this phenomena. So, these important parameters, one is frequency of vibration, next is displacement, next is acceleration, or induced strain or strain. Now, which parameter is to be used depends on the objective of the particular experimentation and also the field of application. For example, if we are measuring the vibration of a system with an objective to figure out what is the source of this vibration, then the best will be to find out the frequency, not amplitude or other things, because in a machine there are many sources of unbalanced forces and moments. There may be various rotating shafts with rotating members, and if the predominant vibrational frequency of the machine happens to be coinciding or matching with one of the rotating members, we know there must be some substantial amount of unbalance present, and that is the source of vibration. So we can rectify the situation. Sometimes, for example, we are interested in analyzing or studying the comfort of drive or comfort of ride in case of a vehicle mechanics problem. So there we have to find out the acceleration to which the passenger or the driver is subjected. So therefore, we will measure the acceleration in such cases, or that will be the predominant parameter. Similarly, if we are investigating the fatigue life of a structural member, then in such cases induced strain or stress will be the predominant parameter. So like that, it depends on what we want to do, what kind of usage will be of our experimental results, that will tell which will be the predominant parameter of measurement. Now vibration measurement is done through transducer. Or in common word we can say pickup. The transducer's job is to sense the vibration say which is a mechanical movement, and produce a proportional electrical signal. Which is proportional to vibration parameter. In general, though there are very rare occasions where we may not use an electrical output of the transducer, but in general, in almost all cases, we get the mechanical motion sensed by the pickup or the transducer, and it transforms that parameter into a proportional electrical signal, which can be then seen or recorded or whatever way we want to utilize it. Sometimes it is used even in an online feedback loop in a machine to do something. So this is the basic function of a transducer, and in these I think sessions what we will do, we will discuss the design and basic principle of some of the commonly used transducers. First thing what we will take up is a very simple problem of frequency measurement. Now, frequency measurement in many situations may come out as a byproduct, like say for example, if we can sense the whole signal, obviously frequency, amplitude, velocity all may be simultaneously sensed. But in simple industrial scenario, quite often a mechanical vibration transducer we can utilize, which will give the frequency. The basic principle is the transverse vibration of a cantilever beam. If this is the cantilever beam, uniform beam of length L, then the natural frequency in the first mode is proportional to 1 by L square that we have seen. This is nothing but omega n by 2 pi. This is the circular natural frequency, this is in hertz, this is in radians per second. So therefore, if we can have an arrangement through which we can adjust L, then its natural frequency will change. And then what we will use? We will use the principle of resonance. If we attach this to the vibrating body, the vibration will be most severe only when the natural frequency of this matches with the actual vibration. And if we can somehow calibrate it, that means for what length, what natural frequency we get, then from that we can figure out what is the frequency of the object to which this has been attached or connected. So simply we will get natural frequency. It is not very accurate because by visual observation it may not be always possible to say when the amplitude of vibration is maximum, but it can be easily augmented by attaching a simple electric pickup signal which gives the vibrational amplitude, and measuring the amplitude by some meter or by some oscilloscope we can do a better estimate. But in a crude way, since the objective is to get some idea about the order of magnitude of the frequency, visual observation is enough. So this vibration pickup called Westinghouse vibration vibrometer is like this. a very simple arrangement. This is a uniform steel scale kind of thing, which is supported by a series of rollers. That means this end may be considered to be equivalent to a fixed end, cantilever end, because the slope and displacement both will be 0 here. Now this one of these is connected to a knob outside, which can be rotated by hand, and this can be made sliding in this direction. Thus, the length or the overhang portion of the length of the overhang portion of this cantilever beam could be adjusted by this, and the reading can be taken here, that what will be the corresponding natural frequency when you touch it to the machine body vibrating, so it will vibrate. So only one thing is we have to keep in mind, that this mechanical vibrometer, the range is from 2 Hertz to 10 Hertz to 250 Hertz. This is the effective range in which it can be utilized. However, when we use this lower range, this range, in this range a standard mass is attached to this, because otherwise this range is so large that it will be essential to change the length of the cantilever portion to very large value, and it will make the length of the whole equipment very large, which may not be always desirable. So what is done, this range is taken care of by this sliding, and then the natural frequency of the whole beam is reduced by attaching a separate mass at the end. We know that if we attach a mass here, immediately the natural frequency will be less. So therefore that brings, again then the length, if we change, it will give us a different scale. So attaching a known mass, known standard mass, so that is the only thing what we have to do. Here one disadvantage is that at higher frequency the sensitivity is less. What is meant by sensitivity is this, that here I think by changing the frequency, if the frequency changes, how much should be the displacement of this. If it is too small, then it becomes insensitive to the frequency. Now it can be easily seen that if we say that natural frequency is proportional to 1 by L square, or we can say natural frequency is equal to some constant by L square, then a small change in natural frequency, this will be equal to minus 2C by L dl. Now from this again we know L is equal to square root of C by mu. If you substitute this here, this will become minus 2 square root of C by square root of mu dl. So how much change is necessary for a change of frequency d sigma can be written now. Will be minus 2C, and L is how much? Square root of C square root of mu dl. So, change in the length is given by minus 1 by 2 square root of C nu d nu. Thus, it is very clear that when we are measuring frequency and frequency is small, then the change of length required for a corresponding change or for change of the frequency, when this is small, this is substantial, but when nu is very large, for a given change in frequency, the change required here will be very small. So, it will be insensitive to this change of frequency at high frequency. So, this is one disadvantage. Secondly, of course, the range of frequency which can be covered is also limited. Now, I think, so therefore, the modern transducer or vibration pickup, if you want to study, first let us see what are the various types or broad classification. The transducers can be classified into contacting type, and non-contact type. Means in non-contact contact type, the transducer is put on the vibrating body or attached to it. On the other hand, the non-contact type is a pickup which does not touch the actual vibrating body, it senses its motion from proximity, from a nearby position. So, this we can do, or we can use contacting type pickup only when putting or attaching the pickup to the main body or the main system which is vibrating does not alter the characteristics of the system itself. So, therefore, for big machines, rugged systems, etc., we can use the contact type vibration pickup because it will not have much effect on the characteristics of the system which we are going to measure. On the other hand, for very delicate systems, very light systems or flexible systems, we cannot put a pickup attached to that because the system's natural behavior is going to change. In such cases, we try to sense the vibration through a non-contact type pickup. And obviously, the limitations also come. So, here, since the pickup is attached to the body, then what is the movement, the amount is not restricted. On the other hand, here it is placed very near the object which is vibrating. So, obviously, it will be possible to measure it properly only for very small movement, because large movement is going to cause problems for this type of vibration pickup. So, both these contacting type and non-contacting type can be further classified into two groups which are passive or active. In passive type pickup, what happens? We don't have to have a separate electrical power source to activate the transducer or to get the result. On the other hand, in active type of vibration pickup, it has to be connected to a separate electrical source for its power, then only it will function. So, both types are there and they have their advantages and disadvantages. So, what we will do now, we will basic principle of certain transducers. So, what the fundamental thing we have to keep in mind is that suppose we use any type of contact or non-contact type of vibration pickup and we attach it to the body of machine or system which is vibrating. So, then the electrical signal what we will get out from this. Generally, this voltage will be proportional to velocity or proportional to acceleration. Generally, these are the two cases what we will get. Then what will happen? This can be computationally integrated or electronically or computationally integrated, and finally we get the information about that is the basic principle. So we will start with the most common type of vibration pickup which are used. They are called seismic vibration pickup. Their basic principle can be understood from the analysis which we have already done for vibration with base excitation, because effectively these pickups are nothing but systems which are excited by the body to which it is attached. I am talking about contact type seismic pickup, and obviously it is nothing but a vibrating system with base excitation. Basic scheme is like this. So this is the basic scheme of the pickup. It is connected to the machine body or system body which is vibrating like this, and we call this vibration as a function of time. Then we know that from equilibrium position, the vibration of the mass we can describe by x, which is a function of time given by x. Now, in such a situation, what we can really sense is the movement of this mass inside this container. That means the relative movement of the mass with the container. Now, the very crude way it can be sensed by putting a scale here and the pointer which is attached to the mass, what movement it moves there, but really that is not the way it is done. What is done, that it is this movement here is sensed by some electromagnetic effect. If we can put a coil and a permanent magnet attached to this, or the other way around, the coil is attached to this and there is a permanent magnet which is fixed to this body, then the relative movement between the coil and the and the core, that will generate a signal. So actually it is done that way. But anyhow, our primary objective is, as you can see, is the measurement or the sensing of the relative movement between the container and this. So this relative movement, what is sensed is Z, a function of time, which is nothing but the relative movement between the two. Now, let us see the free body diagram. This is the mass. At any instant of time, the force, that means if it has gone by x and this has gone by only y, then the compression is given by x minus y, or if we want to say it is, so therefore it will be a into x minus y. Similarly, if this is going by x amount and x dot velocity and this is following by y dot velocity, then the relative velocity with which it is stretching is x dot minus y dot. So, and the force will be c into x dot minus y dot. Gravity we ignore because we know that if everything is considered from the equilibrium position, which is already under the action of gravity, then gravity will not play, everything will get cancelled. So, the equation of motion for this system will be m x 2 dot is equal to minus the now if we subtract m y 2 dot from both the new left and right hand side, or we add minus my 2 dot on both sides, taking m common, or it will be nothing but m z2 dot, because z2 dot is x2 dot minus y2 dot. We take this e into z dot, which is nothing but z dot, plus k into z is equal to minus plus m omega square. If we use y is equal to this is used here. So now, this being the equation of motion, what will be the solution? Now we know in steady state, the solution we can always assume to be another harmonic function of time with the same frequency but at a different phase. So let the solution be if you substitute z in this and equate the coefficients of cosine omega t on both sides and sine omega t on both sides, we will get two things. So, substituting in equation of motion and equating the coefficient to do that we will get now dividing both sides by this quantity which is common and squaring and adding, we get and using the same symbol which we have used so far, this will become nothing but if we divide both the numerator and denominator by k, this becomes omega square by k by m, that is omega n square, that is r square. R is the frequency ratio and the denominator becomes again then 1 minus r square whole square to zeta r square. And tan psi, if we divide this by this, tan psi will be given by so now I think let us see how it looks when we plot the characteristics. If we plot from this z by y characteristics, now you can see that for zeta, that means the damping, for various values of damping the response curve is like, but as we have seen that for in this case when r is very large compared to 1, that is the case we are discussing, then z is equal to y, and as you have seen from this. So, but that really gives excellent result only beyond certain value of r. Now, to get the widest possible range, we should try to see that for which value of damping factor we get z equal to y at the earliest possible value of r, and as you can see that for the damping which is equal to 1 by root 2 or 0.707, the z by y curve approaches 1 at the earliest, and beyond 2.5 we can safely use this as the velocity meter. So, therefore, in this situation the value of natural frequency of the system or the seismograph should be very low, and the frequency which we will measure or the vibration which we will measure must be at a much higher frequency, so that r is much more than 1, and beyond r is equal to 2.5 we can get excellent result if we can match the damping factor to this value. Otherwise also they are all ultimately approaching 1, as we find from the asymptotic tendencies. Now a pickup with low natural frequency, that means the natural frequency of such pickups are generally 2 to 5 Hz. So we should plan to design the seismograph in this range. And one thing also must be noticed, that the damping factor, when we try to adjust, we should try to have as close to zeta is equal to this as possible. Anyhow, now I think let us consider the other extreme case. This extreme case was r much greater than 1. Now let us consider the situation when r is much less than 1. What does it mean? R very less compared to 1 means the frequency of the vibration we are measuring is very low compared to the natural frequency of the system, or in such cases the natural frequency of the vibration pickup will be very high. So that is case 2. R is very small compared to 1. If r is very small compared to 1, then from this what do we find? If r is very small means we can consider this to be 1 and we can ignore this. So therefore denominator becomes 1, and this so the whole denominator becoming 1 means z is approximately equal to r square into y, and we know that or z is approximately equal to omega square y by omega n square, where omega n is the natural frequency of the pickup. Now natural frequency of a particular pickup is a constant quantity, so we can consider to be constant, and this means that the relative movement is proportional to omega square y. Omega square y is nothing but the acceleration of the vibrating body whose vibration we are going to pick up. Thus here we treat these kinds of units as an accelerometer. That means our output of the pickup will be an electric. If this is the pickup mounted on an object which is vibrating, so its acceleration is omega square y, I mean the magnitude of that. If the output of this voltage, that will be proportional to acceleration, and it can be considered as accelerometer, but the conditions what has to be satisfied is that r must be extremely low or omega n must be very high. So omega n will be in megahertz range. Another important thing has to be also kept in mind, that here how do you generate this electric voltage? In the previous case we know we used electromagnetic induction, and thus the voltage was proportional to the velocity. In this case, if the output has to be proportional to acceleration, so one is that this relation has to be approximately valid, which is ensured by this. Second is that the voltage which we generate here, the mechanism of that in transduction should be that where the voltage is generated by displacement or proportional to the displacement of the object, that means z, relative displacement. Now both these conditions are very nicely satisfied by one type of pickup, where this is the mass, inertial mass, mounted on a chain disc of a special kind of material which we call piezoelectric material. This is the container. So, this is the inertial mass. This is the piezoelectric crystal. Now, the property of piezoelectric crystal is that if we have a piezoelectric crystal of thickness say T, then if we subject this to a deformation by subcompressive force, by developing some compressive stress, then a voltage is generated at this. That means if we connect this, voltage E will be generated, which is proportional to the strain. That means which is proportional to this displacement or this So, due to inertia force, which is my2 dot, inertia force is my2 dot, mx2 dot, and this inertia force will cause compression or deformation of this piezoelectric crystal, and that will generate a voltage. And this voltage will be proportional to this strain to which this is subjected. Strain means it is proportional to deformation, because strain is nothing but this deformation divided by the original thickness T. That means which T is constant, so it will be proportional to Z or the displacement. So, the voltage will be proportional to acceleration. So, this type of pickups where the output voltage of the transducer is proportional to the acceleration of the object are called accelerometers. As mentioned here, since the stiffness of this piezoelectric plate can be very high, mass is small, so therefore effectively the natural frequency of this spring mass system, because it is equivalent to a mass supported by a spring, where this spring stiffness is very high, and so the natural frequency will be very high in megahertz range. So, we can measure quite a few tens of kilohertz with the help of this kind of a unit. Now, if we plot the characteristics So, since this is equal to this, so when this will be satisfied, then omega n square z by omega square y will be 1. So, when that happens, if you want to see, so when we plot details, we can see now that here of course our condition is that r has to be very small. Again we should try compared to 1, again we should try to have as much range as possible, and we find the largest range when this relationship is approximately satisfied is obtained when zeta is equal to 0.707 compared to all other possible values. So therefore again zeta equal to 0.707 gives us the range of operation, which is the largest. Otherwise you have to operate very near this, but with 0.707 we can go r to almost 0.3 and still satisfy that very accurately. If we plot the phase, this, if we use some lower value of zeta like this, from this we find when r is very small compared to 1, then tan psi is equal to 2 zeta r. And if that be so, since zeta is never a very large quantity, so tan psi itself is very small. That means psi itself is very small, 1, and that tells us psi is proportional to r. That is why at zeta is equal to 0.707, we will find that we will get this approximate linear relationship the best. Others also will be like this. When r is very small, it will be straight line, but when r is even goes up to 1, it will be approximately a straight line for this particular value of zeta. This has a very important application or important result that we will now see. This proportionality of psi with r helps one to, or helps the transducer to maintain the shape of the signal or the vibration what we are measuring without any distortion. That means the voltage which we will get will be a faithful reproduction of the actual vibration. So for example, so if the original vibration is something like this, then the voltage which will be produced by faithful reproduction will be something like that means the shape will be very similar to the shape of Y. How it happens that we will see. Say the vibration is given by Y, a function of t. If it is periodic but not harmonic exactly, we can represent it through a Fourier series. Where omega 0 is the fundamental frequency. How do you find it out? To find out the period, time period, and omega 0 is equal to so we can easily from the vibration pattern of the basic object which we are investigating, we can find out omega 0. So this will be, so therefore the signal for the pth harmonic will be this signal is proportional to z, that means equal to proportional to omega square y. So omega for the pth harmonic is p omega 0. So it will be p omega 0 square AP y is equal to this AP cosine omega 0 p t minus psi. That is the signal generated by the pth harmonic. Now, if zeta is approximately 0.707, then psi is proportional to r, or we can say psi will be equal to some constant lambda into the frequency, that is omega 0 p, because r is nothing but omega by omega n, and omega is omega 0 p for the pth harmonic. So if we write it here, or the signal for the pth harmonic which we get is now if we use psi is equal to lambda omega 0 p and omega 0 p we take common outside, it will be simply where lambda is a constant, and the total signal will be sum total of all the harmonics. And if this be the vibration, what will be the acceleration? Double derivative of this, that is y2 dot p acceleration is so comparing these two, we find that even if the vibration is not harmonic but periodic, the acceleration pattern and the voltage generated, that pattern, they are same, only there is a slight shift in the origin of the t, that is all, but the shape is undistorted. So that is one great advantage, and since accelerometers are used quite extensively, this property helps in the analysis. So therefore we find that this seismic type of pickups can be primarily of two types. They are both contact type pickups, as you can see, and they are also both we will see they are both passive, that means they do not require any outside power source. In the one extreme case, like when R is, that means the natural frequency of the system is very low, in such cases it is treated as a velocity meter if the velocity or the voltage is generated by electromagnetic induction. On the other case, when the natural frequency of the system is very high and the operational frequency is generally very low compared to that, then what we generate as a voltage using piezoelectric pickup, which will be proportional to the acceleration of the system, and they are called accelerometers. Accelerometers by nature, because the whole thing can be very small and coincide, they are very small in the form of buttons. On the other hand, the velocity type seismic pickup are somewhat bulky. In the next presentation, we will discuss other types of transducers and vibration pickup.